All right, so welcome to chapter 15, chemical equilibrium. All right, now we've heard the word equilibrium a little bit before, and you might remember more or less what the word means in terms of chemistry. Specifically, what we're looking at here is dynamic equilibrium, which means that if I have a chemical reaction like this one shown here, where I have one chemical, this is acetic acid, and here's another chemical, water, combining together, producing these products. So in this reaction, we can see that the acid here, which has a proton, hydrogen with it, releases that proton to water and forms the hydronium ion, and we have the acetate ion that's left over as well as the hydrogen leaves and joins the water. All right, so this is the first time, when we first introduced equilibrium, we were talking about it in terms of weak acids, and this is a weak acid, right? Now a strong acid, if you remember, right, something like HCl, if we take a strong acid, it was generally showed to do something like this, or if you wanted to have the water involved, we would show it like this. Now again, the reason why we only put single arrows is because it being a strong acid, right? And it's always good to have a review of what the strong acids are. There are the 7 strong acids, and we won't go over that right now, but we'll have a chapter coming up on strong acids as well, where we have to become familiar with them. But strong acids go to completion. That's what we mean by strong. We mean that they completely dissociate. An acid is a molecular chemical that when it dissociates, it releases a hydrogen ion, right? And that's what we have here. And we can draw it with water, and we can represent the hydrogen ion as a hydronium ion if we like. All right? But this scenario up here is a weak acid. So in weak acids, right, when there are weak acids, a weak acid is an acid that doesn't dissociate completely. In fact, if you were to take a container of a weak acid, so let's say I have HC2H3O2, which is acetic acid, right? If I had a container of this acid here, right, and I wanted to, here it is, and maybe it has some concentration, we'll say 1 molar, all right? I have a container of acetic acid, has 1 molar. If we were to look inside this bottle, we would see, first of all, it's 1 molar in water, so there's lots of water. And then there's some hydrogen ions floating around because they dissociate, as we see here in this reaction, right? We have the acetate ion, C2H3O2 minus, floating around. But then we'd also have some of the acetic acid itself, the non-dissociated form, floating around. So I'm going to sneak this in here, HC2H3O2. So I'm trying to show that we have some of that in there as well inside the bottle. In fact, if we were to freeze the acetic acid at any one moment, we would look and count up how much of each of these components we'd have. We'd have most of the non-dissociated acid. Okay? There would be very few, relatively, of the dissociated acid. In fact, less than 1% of any of the acid molecules will be dissociated at one time. And that is what a weak acid is. Okay? So we've heard about equilibrium before when we're talking about weak acids. We've introduced it before. And this is a little bit of a reminder. And now we're going to talk more about this equilibrium. Now, before we move forward, we have to recognize that this double arrow is essentially saying that these reactants come together to form these products, but also you can think of these 2 products as reactants, because when they find each other, there's a rate at which they will form these products, these which are drawn here as reactants, but they would be products if you look at the reaction heading to the left here. Okay? And the rates at which these reactions occur would determine how much of each of these components, how much of the reactants, and how much of the products, as we have it drawn here, would be present at any one given time. Okay? So there's a couple of ways we can draw our reversible arrows. Either one's okay. All right, so let's think about this. Here's another example of an equilibrium reaction where we have this chemical being converted to two of these molecules, right? So essentially, in this scenario, we start off, if we plot our concentration here on the y-axis versus time, we start off with an amount of our dinitrogen tetraoxide, right? And we start off with 0 of this nitrogen dioxide, okay? So the red line here plots the concentration over time of the dinitrogen tetraoxide, and this plots the concentration of the nitrogen dioxide. All right, so initially there's no nitrogen dioxide, and the reaction begins, and initially the reverse reaction, two NO2s coming together to form this, can't occur, right? It can't occur initially because there's none of it, right? That's what this blue line is showing here. There's none of it, right? This is the only reaction that can occur. Now, as soon as this reaction begins to occur and we begin to accumulate some of this material, then the reverse reaction can begin. All right? So the concentration of the N2O4 goes down initially, right, as the reaction proceeds, and the concentration of the NO2 goes up initially as the reaction proceeds. But then there comes a point where the rate at which this stuff decomposes into nitrogen dioxide is the same as the rate at which the nitrogen dioxide molecules come together to form the N2O4. All right? And when that occurs, then you get an equilibrium. You get an equilibrium. And so here we say we've reached equilibrium at this dotted line, and from this point on, the relative concentration of N2O4 and NO2 are going to stay pretty much the same. The concentrations aren't going to change much. All right? Now, that doesn't mean the reaction stops trying to go to the right and stops trying to go to the left. The processes continue to occur over and over and over, but just at any one given time after you've reached equilibrium, the resulting concentrations do not change over time. Okay? So, well, let's watch this video, see if we can kind of get a handle on what we're seeing here. Let's get this idea.
When heated in a closed system, calcium carbonate will decompose to form calcium oxide and carbon dioxide. As the amounts of calcium oxide and carbon dioxide increase, a reverse reaction occurs, and calcium carbonate is resynthesized. When the decomposition rate of calcium carbonate equals the synthesizing rate of calcium oxide and carbon dioxide, the system is said to be at dynamic equilibrium. Now suppose most of the carbon dioxide is removed from the system, and the system is resealed. The rate of synthesis of calcium carbonate from calcium oxide and carbon dioxide will slow down and almost stop.
Okay, so
however, the decomposition,
if we have less of the carbon dioxide in the container, if we've opened it up and let some out, then the rate at which the reaction will head to the left, right, it decreases, because as we've seen, the rate of the reaction is usually or frequently dependent on the concentration of material that you have. I mean, so if we don't have any carbon dioxide, or if we have very little amount, then the rate of this reaction going to the left decreases. All right? And so by opening up the container and letting out the carbon dioxide, then we slow down the rate at which the reaction can head to the left. Right? Now the reaction going to the right will continue to go as long as there's some calcium carbonate around. This is a reaction which is only dependent on the presence of this stuff. So as long as there's some, then the reaction will proceed to the right. Okay, but the reaction going to the left needs the calcium oxide and the carbon dioxide. All right, so you need to have both of those for the reaction to proceed to the left. So this changes the concentrations of the different components at equilibrium when we remove some of the carbon dioxide. If you think about it, removing the carbon dioxide here will result in less of this being around, right? Because when this decomposes now, there's fewer carbon dioxide molecules to have form back with the calcium oxide to form the calcium carbonate. All right, so we let the calcium oxide out, and it decreases the amount of this, right? And it shifts, what we say shift, the equilibrium to the right, meaning the compounds on the right are going to become more prevalent now than they were at the initial unequilibrated condition. All right, so a review. We started with this stuff. This reaction proceeded to the right. When these found each other, they proceeded to go back to the left. The process continued, and we had dynamic equilibrium. We reached dynamic equilibrium. We then altered the equilibrium by removing some of the carbon dioxide. When we remove the carbon dioxide, then the equilibrium shifts. More of this will decompose, less of the process to the left will occur, and in the end, as we shift, as we remove, for example, remove some of this product here, we shift the amount of this calcium carbonate in the condition. It decreases, while the concentration of this one is going to increase. Okay? Let's watch the rest of this.
Of calcium carbonate to form more calcium oxide
Calcium
and carbon
carbonate to
dioxide
form
will
more
continue.
calcium oxide and carbon
As the
dioxide
level
will
of carbon
continue.
dioxide increases,
As the level of carbon dioxide increases, the reverse synthesis of calcium carbonate will again begin.
The decomposition reaction rate will
Eventually,
equal
the
synthesis
decomposition reaction rate
and
will equal the
equilibrium
synthesis
will be
reaction rate,
reestablished.
and
But
equilibrium will
because
be
some of the
reestablished.
reactants were removed, the
But because some of the
equilibrium has shifted.
reactants were removed, the equilibrium has shifted.
Shifted to the product's side, right? All right. So we need a way to express this equilibrium. It becomes an important enough thing in the world of chemistry, in the world of nature, everywhere. Equilibrium is occurring always, and understanding that equilibrium is necessary for solving essentially every biological problem, for example. Biology is all about equilibrium. Every chemical reaction that occurs in biology has a degree of equilibrium and kind of balances itself that way. And when you get out of balance, then you have some sort of a disease or some sort of a disorder, and restoring that balance is generally done by shifting the equilibrium of a chemical reaction in your body some way. Okay, so it's vital to understand this equilibrium if you want to go on and, for example, make a medicine that will address a certain condition. You need to be able to understand how that equilibrium is affected and how to affect it with your medicine. Right? All right, so we need a way to effectively show what the equilibrium is in a given chemical reaction. So, for example, if I have this chemical reaction here, where I have A plus B going to C plus D, all right, and I can show that this reaction is in equilibrium by having a double arrow. Now the little a's here are the coefficients, all right? They're the coefficients on the larger A. The A being the kind of chemical, right? The large A being the chemical A, large B being chemical B, and so forth. The little letters A, B, C, and D are the coefficients, all right? So you can have, a way to kind of express equilibrium. You could say, oh, the equilibrium, if you wanted to come up with a clever way to communicate with each other what the equilibrium of this given reaction was, I could tell you, well, if the concentration of C is 10 times that of the concentration of B, while the concentration of D is 1/5 that of the concentration of A, at equilibrium, right? So essentially that would mean you put in some A and put in some B, then the reaction would occur back and forth until you reach those equilibrium conditions that I described. But what we need is one number. We need one number that can tell people right away what the equilibrium conditions of this chemical reaction are. And this number we use a quotient. We use a quotient. Now a quotient just means the answer to a division problem. Okay? So Q stands for quotient here. And the quotient for any given equilibrium expression is the product's concentration, and we show that by putting the chemical formula for the chemical inside brackets. So when I say A, that's the chemical A, and when I say A in brackets like this, that's the concentration of A, meaning usually in molar concentration. Now if it's a gas, I can express the concentration of a gas simply by expressing its pressure as well. So sometimes you'll see the pressure of A, something like that. The pressure of A. Well, it's not exactly like that. Usually the P is a little bit bigger or something like that. Pressure of A. All right? But if I have, for example, here is a chemical, HCl, that's hydrochloric acid. If I want to say the concentration of hydrochloric acid, I just put that in brackets like that, and that's my way of expressing the concentration of hydrochloric acid. So when I have, as written up here, this quotient, this means the concentration of C times the concentration of D over the concentration of A times the concentration of B. So essentially what I've done here is I've taken the concentration of the products, multiplied them together, so it's the product of the products concentration, over the product, the multiplication result of the reactants concentration. Now these concentrations are all raised to their coefficient. And this is what we call the equilibrium quotient. Now, Q might not necessarily be at equilibrium, right? Initially, when you're given a reaction, it might not be at equilibrium. For example, if I have a chemical reaction of a weak acid, I say, okay, I'm going to put in this chemical reaction. I'm going to put in this weak acid in, HC2H3O2. This is our acetic acid again. All right, I'm going to put that in with water. And the products of this reaction are going to be, again, H3O plus and C2H3O2 minus, the acetate ion. All right, I'm going to show that this is a chemical reaction at equilibrium. And then I'm going to show you my bottle where I'm actually performing this chemical reaction here, okay? So, and then I can start describing this chemical reaction to people. I can say, for example, all right, I initially start off this reaction just by putting acetic acid and water together. I put them in here. Now, as soon as I do that, as soon as I put them into my container, initially, there's none of these two things, right? Because they can't react until I mix them. So initially, there's none. But as soon as I mix them, then these concentrations, the concentrations of these components begin to increase, right? And then we get the equilibrium concentration occurring as described in this graph here, where the product's concentration increases and the reactant's concentration decreases. But if it's in equilibrium, then the reactants don't completely go away because the products are forming the reactants, and the products don't completely monopolize the system. They don't just predominate necessarily. They may be higher in concentration, but not necessarily. It's just again in equilibrium. So Q refers to the quotient at any given moment. So if, for example, I say, okay, I'm going to put this in, and I'm going to put this in, and right at the beginning, I want to know what the quotient is for this reaction. Well, if I put in 1 mole of this and 50 moles of this, for example, all right, initially there's no moles of these components, right? So the quotient at the initial point would be, my quotient would be expressed as the concentration of the products, so that's H3O plus its concentration, times the concentration of C2H3O2 minus, over the concentration of the reactants. All right, so that's HC2H3O2, and I would say the concentration of water. Now, this would be the initial equilibrium. Now, for now, I'm going to include water. I'll show you later that water is not supposed to be included, and I'll express why, but right now, for simplicity, I'll include it. Okay? So I could say that Q is the quotient for the initial conditions. All right? Now, this actual value here would be what? 50 times 1 over 0, right? So 50 divided by 0. That's, oh no, sorry. The initial concentration here is 0 on top, right? The concentration of this is 0. Concentration of this is 0. All right? Over 50 times, or 1 times 50. All right? So that value is 0. So at the initial Q for this reaction, the value is 0, meaning that there's no products formed. So we see that when we have a low number like that, 0 or something very small, then that means there's no products formed, which makes sense because the quotient is the concentration of the products over the concentration of the reactants. Now my coefficients for all of these chemicals were all 1. So I didn't show that the quotient here had these chemicals raised to the 1, but I could do that as well. All right? So that's a little example of how we can use the quotient of the concentrations of the products over the concentrations of the reactants to show where the equilibrium is at that current condition. Now, if I let the reaction go for a while, so this is time equals 0, meaning at the beginning of the reaction. If I let the reaction go maybe 10 seconds or 10 minutes or some value, then everything equilibrates, right? So some of this reacts to form products. These products react to form more reactants, right? They go back and forth until their concentrations become stabilized, right? Then maybe this is going to be 0.5. This one here, or let's see, this one here would be 0.5 as well. And this one here would be 45.5, and this one here would be 0.5, right? There we go. So, maybe after 10 seconds, this happens to the reaction. And maybe after that amount of time, we've actually reached equilibrium. Then if we've reached equilibrium under those conditions, then you could make a new quotient, and the quotient, when you've actually really reached equilibrium, is no longer called Q, but we actually call it K. K, meaning that we've reached equilibrium. So K is a special Q. When a Q kind of comes to age and graduates and moves on in life, it becomes K, which means the quotient at equilibrium. All right. So we would like you to write the mass action expression for this following chemical equation. All right? So push pause, take a few seconds, write it. You can honestly push pause and take a few seconds and write it. You're not going to learn if you don't. All right, I'm going to show it to you now. Hopefully you push pause. All right, so we have our chemical reaction, right? 2NO2 going to N2O4. All right. The quotient, the mass action expression, another name for the quotient. The quotient here is the products, N2O4, their concentration, raised to the coefficient, which is 1 here, over the reactants, NO2, raised to its, or the concentration of the reactants, raised to its coefficient. All right? So that is going to be our mass action expression, another name for the quotient. Mass action expression. All right, mass action expression. All right, let's try this one again. Here's another chance for you to write it out. Let's see if you can do it. Push pause, take a second. All right. Here we go. So, for this one here, we have the products, carbon dioxide raised to the power of 2 over the concentration of the reactants, right? And the carbon monoxide is raised to the power of 2 because of this coefficient. Here, oxygen is raised to the power of 1 because it just has a 1 in front. All right. Let's see if you can get this one now. All right. Push pause if you haven't. I'm going to show it to you now. All right. Hopefully you got this value here. Same idea, right? Raised to the third this time because this was coefficient of 3. All right. So can you identify which one is the correct mass action expression for this chemical reaction? Take a few seconds. Push pause. Take a look at it for a while. Okay. I'm going to show you now. All right, so this one's correct because it has the products. They're not raised to anything. B and C didn't have them raised to anything, but C had the products in the denominator. The denominator is the bottom, right? C has the products on the denominator. That's not correct, right? Here we have the reactants in the denominator, which is correct. Here are the products in the numerator. And here we have the concentration of copper ion being raised to its coefficient 1, and the concentration of ammonia being raised to the fourth power. All right. Excellent. So, K is the special equilibrium when it's the special quotient, when the chemical reaction has reached equilibrium. So Q is K when the chemical reaction reaches equilibrium. Okay? And again, K is an expression that is of a concentration. For example, if I have a chemical reaction here where I have A going to B plus C, some sort of decomposition reaction, all right? Maybe I'll throw in some coefficients here. Then the equilibrium expression is the concentrations of products, the products multiplied together, raised to their coefficients, over the concentration of the reactants raised to its coefficient at equilibrium. So K is that equilibrium mass action expression at equilibrium. If I was just given initial conditions and I wanted to find out what the initial quotient was, then I wouldn't want to call this the K, I would call it Q. Now, the C here, the little C here, says that we're talking about the concentrations of these in molar units. All right, so concentrations of chemicals can be expressed, as I mentioned, in either molar units, or they might be expressed in just terms of pressure of gas, because if you just have gases, then identifying the molarity of those gases is kind of less effective than just utilizing the pressure of those gases in the reaction conditions. All right, so if we take a chemical reaction like this one here, well, let's go a little bit simpler. Start off with let's use a simpler chemical reaction. If we take a simple chemical reaction here, A going to B, all right? We say it's at equilibrium, and I want to express the quotient that we would use to express the value to tell me about this equilibrium, and maybe that quotient was under equilibrium conditions. Therefore, Q, let me throw in some coefficients or some coefficients here to make sure that we understand how to use the coefficients in the equilibrium expression. Again, I would say the products, that's B, concentration raised to its coefficient, right, over the reactants raised to its coefficient. All right. Now you can see that if this equilibrium, if you start off with 2A in a bottle, and if most of it goes to 3B, and for example here, let me show you my bottle here, right? Here I have a bottle. If I have a reaction where I put in 2A, and then immediately the 2A consumes itself, and most of it goes to 3B, if the rate of this reaction here is fast compared to the rate of this reaction, then, for example, if I'm going to plot the concentration of A here, its concentration versus time. Its concentration is going to go down, right? And if this is the concentration of B on this line here, its concentration is going to go up. And when, again, the rate of B going back to A is equal to the rate of A going back to B, we'll find an equilibrium. It'll be at equilibrium, and the concentrations won't change much. So it depends on the rate of the reaction. If the rate of the reaction is such that the concentration of A going to B is very fast, but the concentration of B going back to A is slower, then A will run itself very low in terms of concentration, and B will be predominant, right? You could also have a scenario where the same thing, same chemical reaction, but the rate of decomposition to B is slow, therefore it stabilizes quicker, and the rate of concentration of B can be converted to A is also slow. Therefore, slower, right? Then your equilibrium concentrations will be different, right? If this is the kind of scenario you have here, where you have lots of products at equilibrium, right? And this is the expression at equilibrium, then this will be a large number. If the chemical reaction that I've drawn here has a K that's large, like 10,000, right? That shows me that this reaction, when it reaches equilibrium, has a lot of products. On the other hand, if I say that the K for this reaction equals, so this is my one example for 10,000, if my K for this reaction equals maybe 0.05, a very low value, that indicates that when the chemical reaction reaches equilibrium, it has very little relative, small amount of products compared to reactants. Okay? So, the K, the size of the K, whether it's a large K or a small K, tells you immediately about the equilibrium conditions that are met or that are reached for a given chemical reaction. All right? Now, so here is this chemical reaction here, or here's the equilibrium expression for this chemical reaction. The same thing can be done by looking at the, let's see, let's look at how much. The same thing can be done. Let me rewrite the equilibrium or the chemical reaction here. Okay, so if I have this chemical reaction here, and I'm going to write the K. All right. Another interesting thing, or another thing that you have to become aware of, is that if I take this chemical reaction and I draw it in the reverse way, so 3B going to 2A, and show that this is an equilibrium, the resulting K is going to be what? Products now, which are A, its concentration raised to its coefficient, reactants, its concentration raised to its coefficient. So, I have these two reactions. It's really the same reaction, just drawn differently, right? Well, the resulting K, when you compare the two, are just the inverse of each other, right? So when you reverse a reaction, the K is inverted. An even simpler scenario, if I just have A going to something like C, and then I show C going to something like A, the K for this reaction would be concentration of C over the concentration of A, and the K for this reaction would be the concentration of A over the concentration of C. Right? So, when you reverse a reaction, the K just inverts. All right? So, if this K had a value, a number of actually 3, then this K here would be, again, the inverse of that, or 1/3. Right? Okay. So, again, a number 3 means that the relative concentration of the products is higher than the reactants. A number less than 1 shows you that generally the products are going to be lower relative to the concentration of the reactants. So again, a higher number means that this equilibrium lies to the right. Whoops, I forgot to write the equilibrium arrows in. And a lower number means this equilibrium, its concentration lies to the left. Higher concentration of this scenario, higher concentration of product. All right, good. Now, let's go ahead and answer this question. All right. So, here we have a chemical reaction. The Kc is 500. All right, the Kc is 500. That tells you right away something about the relative concentrations of the ammonia, and compared, so the ammonia, this is the ammonia, right? Compared to that of the hydrogen and nitrogen gases. All right, now we have to answer the question, which would be, what is the Kc for this reaction below, which is the reverse reaction? All right, so do you know what the value would be? Take about 5 seconds, see if you can, or take as much time as necessary. Push pause right now, see if you can answer it. And I'm going to tell you what's going on here. All right, if we draw, I'm going to show you now, so push pause if you haven't taken a stab at it yet. If we write the K for this expression, it's the concentration of, whoops, not two, concentration of products, let me try again here. K equals concentration of the product, NH3, raised to its coefficient, over the concentration of the reactants, raised to their coefficients. That's the K for this top reaction here. And apparently that the resulting value, when you look at the concentrations and divide them all out, raise them to their powers and divide them out, equals 500. Therefore, if we have a reverse reaction here, all right, if we have a reverse reaction here, then the resulting K for the reverse reaction is N2 times H2 to the third over the concentration of ammonia squared. All right, and so now this value here is going to be the inverse of 500, or 1 over 500, or 0.002. All right, now what would happen if I have this same chemical reaction here, but now my coefficients are different? My coefficients are different. You can see that in this chemical reaction that's provided, all of the coefficients are divided by 2. All right. Now, before you jump to any conclusions and say, oh, you just take the K and divide by 2, let's take a scenario and try to answer the question for ourselves by using an example. So what we're going to do here is we're going to use the example of A going to B, and then 2A going to 2B. All right. The K for this one is the expression, the equilibrium expression for this one will be the concentration of B over the concentration of A. All right. The expression for this one will be the concentration of B squared over the concentration of A squared. All right. So this, if you remember in Math 110, means, or is the same, can be expressed as also concentration of B over the concentration of A, and that whole quantity squared. All right. So how do these two compare to each other? If you raise, or if you increase the amounts of the materials, have increased coefficient, then that raises the exponent, and the resulting K, let's say this is 500, no, well, let's just say it's 10 for my specific example here. But that would mean this one here would have to have a K of 100. So for this scenario here, where this is 500, this one would be not squared, but what? It'd be the square root. So the square root of 500 should be 22. All right. Now, as I mentioned, equilibrium concentrations can be expressed in terms of pressure. well. All right. So if I have pressure, if I'm just talking about an equilibrium, a reaction that is just gases, and this is my equilibrium expression for that previous reaction. Almost. It looks like I have a little bit of an error here. It looks like this is supposed to be raised to the 3. Let's see if I can take care of that really quick. Nope, I can't. Won't let me in right now. Okay, so this is supposed to be raised to the 3 here, but that's all right. All right, so what we're trying to get out of this slide is this is the equilibrium expression in terms of molarity. So if you're talking about the molarity of these different concentrations, then we would call it Kc. But we can also express a reaction in terms of pressure, because as we know, when we had our gas chapter on gas laws, we saw that if you have a chemical reaction that's all gaseous, then you can use the chemical stoichiometry. You can use the chemical stoichiometry as either molarity or also in terms of concentrations. For example, here's my chemical reaction up here. This says, we could translate this into English, a mole of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia gas. I could also, because again, the concentration of the gases are directly proportional to the pressures, I could say, well, this could also mean 1 atmosphere of nitrogen gas plus 3 atmospheres of hydrogen gas yields 2 atmospheres of ammonia. Okay, remember that? Well, that K value being expressed not in concentration in terms of molarity, but in concentration in terms of pressure, the resulting K value here could be expressed in this way, where you have the pressure of ammonia, again squared, the pressure of nitrogen gas to the 1 power, because the exponent was 1, and the pressure of hydrogen gas, which was supposed to be to the 3rd, but to see that it's the same as this one, we just have it to the 2nd power. And there's an equation to relate the K under concentration molarity and K under concentration when you refer to them as pressure. Okay? And this is an equation that you're not going to have to memorize. It'll be provided for you on your data sheet in an exam. But you need to know how to recognize it and use it. Okay? So essentially here we have Kc and Kp. Kc is the concentration or the equilibrium constant value under units utilized as molarity for concentration of the components. And Kp is the constant expression, constant value under where the components concentration are expressed as pressure. R is our gas constant, 0.0821. T is the temperature in Kelvin, and delta N. Delta N is the change in the moles of gas. So you're going to look at this. N we've used as a value, as a variable for moles before, and you're going to have to be able to remember that N is the change in moles of gas, meaning the products, moles of gases in the products minus the moles of gas in the reactant. So let's show how this is done. So here's the chemical reaction. If the Kp for the reaction is known to be 0.48 at 25 degrees Celsius, what is the Kc for the reaction at the same temperature? All right. Go back to this slide, get this equation down here, right? And then try to apply it to this problem. See if you can apply it to this problem, right? So here's our equation. I'll give you a few moments. You push pause and take a look at it. Okay, hopefully you gave it a shot. Now, our Kp value is given to us as 0.48. Our Kc value, we can solve for Kc if you want to do that first. Our Kc value would be Kp over 0.0821. That's our R, times the temperature. Now it has to be in Kelvin, so that's 25 plus 273, that's 298 Kelvin. All right, raised to the power of delta N. Now, delta N is the change in the number of moles of gas. So the number of moles here in the products, well, this is just 1 mole of gas expressed here, minus the moles of gas in the reactants, that's 2. So 1 minus 2 is a minus 1. So this would be to the minus 1 here. So we would put that into our calculator. Now, you got to make sure you know how to let me get my calculator here. You got to make sure you know how to put these in your calculator and get the right answer out. So take a second if you haven't done so. Push pause again. Try to get your calculator to spit out the right values. Okay, so let's see if we can get 11.7 to spit out here. Excuse me. So I'm going to do the R, 0.0821, times the 298, and get that value down below, and then I'm going to raise that to the negative 1. All right, there's that value. And then I'm going to take my 0.48, which is the Kp, and divide it by that value that I just got, and I get 11.74. All right, great. Okay, here's another scenario. If the Kc of the reaction is 0.99 at 25 degrees Celsius, what's Kp? All right, see if you can take a second to do that one. All right, hopefully you push pause and you took a second to do it. Again, our K, whoops, I thought it would show us an equation. Our Kp equals Kc divided by RT raised to the delta N. All right, they told us that Kc here was 0.99. We're trying to solve for our Kp. Divided by 0.0821, we have 298 Kelvin again, 25 degrees Celsius, and this has to be raised to the change in N. So in this scenario here, we have 4 moles of gas in the products, and again, change in N equals N in the products minus N in the reactants. Another way of remembering this is N final, moles of gas final minus N initial. All right. All right, so 4 minus 3, this is going to be raised to the 1. All right, so I'm going to put in my 0.0821 times my 298. That's raised to the 1, so I don't have to do anything there. 0.99 divided by that value. So, whoops. Sorry about that. It's not divided by, this is multiplied by Kc times RT. So, let's try that again. Here's our, let's see, no. There's our 0.821 times our 298. Now we can multiply this by 0.99. All right, so that gives us our 24. Okay, there we go. Excellent. All right, so it's not Kp equals Kc times RT delta N. All right, and again, I get out one of the ACS exams here, and you'll see that on the in the ACS exam, they'll give us a bunch of chemical equations, and one of these will be, where's it at? Maybe this wasn't a good idea. I can't see it here. If they don't give it to you here, then they'll have to give it to you in the specific problem. Okay, but that won't be one that you'll need to memorize. Okay, so on we go. Now, the equilibrium constant, for a solution, doesn't generally change if you add more of something to a reaction, like if you add more to a reaction of chemical units that are solid or liquid. So let me give you an example here. If I have a chemical reaction here where A combines with B to form C and D, and this is in some equilibrium. If now I'm going to draw a little container to kind of give you an idea of what's going on here. I have A and I have B, right? I'm putting them into the container. They start forming C and D. And as C and D are formed, then the reaction goes backwards and they end up forming more A and B. Now, the equilibrium expression, K, or the quotient, Q if it's not quite at equilibrium, the equilibrium expression is always trying to tell us what the relative concentrations of these components are as at equilibrium. All right? If this one here, for example, if B is a liquid, all right, and A is maybe aqueous, maybe B is the water or whatever, A is aqueous and B is a liquid, and I put these in here to start off with, all right, the concentration of B, even if A reacts with B, the concentration of B is going to be so high relative to the concentration of A that its concentration isn't going to change. In fact, if I add more of it, it's not going to increase the amount of change the concentration of B. If I remove some of it, it's not going to change the relative concentration of B compared to A. All right. Same thing if it's a solid. If it was a solid. All right. So here's another scenario here, where I have some D combining with E to form F and G. If E here is a solid and D is maybe gaseous, all right. In this container here, I have some D floating around gaseous-like, and then I have a pile of solid, E, right? If I put more solid in here, I would think, oh, I put more in so the reaction can happen faster. But it doesn't actually change the reaction. If you add more liquid or more solid into a chemical reaction, it doesn't change the rate of the reaction occurs because it's not changing relatively very much the concentration of the component. Yes, I put more in, but I'm actually covering up a bunch of the solid there as well. Okay? And we saw this before, where we saw that the rate of a chemical reaction is related to the surface area of the chemicals that are reacting, right? If we just add more solid into a reaction, a solid you could think of something that's kind of dissolved and floating around, but it's not. It's particles whose surface can react, but the inside can't react, right? So because of that, we never include solids or liquids in the equilibrium expression. So if these were both aqueous, put in some coefficients here to remind us how the coefficients should be treated. The equilibrium expression for this would be products, concentration of C, concentration of D, raised to their coefficients, over reactants, concentration of A, raised to its coefficient. But I wouldn't include B in the equilibrium expression. And that's because, again, its concentration will not effectively change the equilibrium at all. Okay? So, we're interested in this expression here because this expression tells us how the equilibrium of a reaction proceeds, and it will also tell us how it shifts based on certain changes, like altering their concentrations of these reactants or products. So for this one here, the K for this one here would be the concentration of the products. Let's say if these are gaseous. concentration of the products, F and G, over the concentration of the reactants, but I would not include E because E is a solid. So, long explanation short, you don't include solids or liquids, right, in the equilibrium expressions for chemical reactions. All right, so can you write down the mass expression for this chemical reaction, right? The mass action expression, the Q. All right, take a second. Okay, push pause, write it down. Here we go. The mass action expression would be like this, right? The concentration of the products is not included because it's a solid, but the concentration of the reactants are. So then we just have 1 over the concentration of the reactants. Here's another one. Take your time and write this one. All right, hopefully you push pause and take your time and wrote it. Here we have the concentrations of products, both being included, but the concentration of the water in the reactants is not included. Again, because as you increase the amount of water, it doesn't increase its concentration of available water, right? All right, let's see. Here's another one. Which one of these is right? Take your time, answer it, push pause. All right, so hopefully you took a second to look at this one. It wouldn't be A, right? Because A would not include the calcium phosphate, the products here, right? It wouldn't be A because that would not include that. It wouldn't be C either, right? Another problem with C is that, or no, A, another problem with A is that the product is in the denominator, which is not right. But it wouldn't be C either because the products wouldn't be included. Now, products should be in the numerator, but it's just going to be expressed or replaced with a 1 in this scenario. So D is going to be D is going to be our answer, right? D is going to be our answer. All right. So we have our expression where we include only the concentrations of the aqueous or gaseous components, not solid or liquids. All right, one more chance. All right, again, if our answer here is D and we're looking for the reverse reaction, it's just going to be the reciprocal, right? The reciprocal, meaning we've changed the numerator and the denominator. Okay, so we talked already a little bit about this, but we want to identify what the significance of these numbers that would result from these expressions. All right. So if we had actual concentrations of material, of reactants in a reaction, and the resulting K from that reaction. So for example, as I said, if I have A going to B, and I have a K value for this reaction, if the K value is large, like 10,000 or something like that, then that tells me the relative amount of concentration of B, products here, which is B, is high, because that value, 10,000, would be what the concentration of the products are over the concentration of the reactants. And if this is a large number, then that means there's lots of products compared to reactants. All right? If the K for this reaction here was 0.03, very small, for example, still it's talking about the concentration of B over the concentration of A, right? Therefore, in this, under those conditions, the equilibrium favors the reactants. So large value means the equilibrium favors the products. Small value means favors the reactants. Equilibrium favors the reactants. Now, what does it mean when we say equilibrium favors something? All that means is that the concentration of that side, the reactants or the products, is higher compared to the concentration of the other side. Okay, so here's a chemical reaction. If we have the Kp for the reaction and we know it's 0.48 at 25 degrees Celsius, does the reaction favor products or reactants at this temperature? Well, if K equals 0.48, what does that tell you? That means the relative amount of products is small compared to the relative amount of reactants, right? So this would mean that the reaction favors the reactants as opposed and not the products. Okay? However, because the value is not terribly small, now we'll go back to this slide back here. If the value is between 10 to the minus third and 10 to the third, then there's some of each. All right, so when you're close to 1, for example, like what would 1 mean here? If K equaled 1, what would that tell you about the concentration of the reactants over products? It would mean that they're the same, right? So essentially, you had a chemical reaction and you monitored the concentration of A versus time, and it went like this, it decreased like that, and you monitor the concentration of B versus time products, and it would go like this until they had the same concentration, right, for this scenario here. Okay? And at those conditions, the rate of B becoming A is the same as the rate as A becoming B. Okay. So here are some equilibrium constants for a reaction, an acid and water. And what is the more efficient reaction? Now, what does efficient mean? Efficient means I have some chemical reaction. Now, this is an acid and water, so I'll say HA. A represents the acid, H represents its proton. And if I'm going to dissociate that acid into the water, then I'm going to get A minus and H plus. All right. So here's the acid, here's its dissociated form. It's in equilibrium though, because it's telling us that there's a Ka associated with it. Now Ka refers specifically to the dissociation of A, meaning acid, right? Ka is the equilibrium constant for that acid. And because if I'm talking about the equilibrium constant for a weak acid like this, it shows the concentration of the products over the concentration of the reactants. It's telling me how much of this will actually dissociate into the dissociated form. How much of it will go into the dissociated form. All right? So if I have a very large value, then that means that the acid is very effective or efficient at dissociating. So efficiency means how well the reaction proceeds to the right, proceeds to the product's side. So I can look at these K values and see which one is larger, and the larger ones will be the ones that are associated with the more efficient reaction or the stronger reaction. So it looks like 6.3 times 10 to the minus 3 will be our most efficient reaction, right? Okay, very good. So that's a good place to stop for this first day. All right. So thanks for watching.